section 5.6. This is what I'm going to call top heavy. So the numerator and the degree in the numerator is larger than the degree in the denominator. And we'll see what happens right now. So let's start with step number 1, our vertical asymptote. So vertical asymptote happens when our function is undefined. So to find it, we're going to set our denominator equal to 0. So x plus 1 is equal to 0. Our vertical asymptote is x equals -1. So here, let's start graphing it. So x equals -1 is going to be right down this way. So vertical asymptote at x equals -1. And next, we're going to do our horizontal asymptote. Horizontal asymptote is determined by the end behavior. So what we're going to do is set y equal to the leading degree in the numerator divided by the leading degree in the denominator. So 2x squared over x. These simplify to just be, 2x. That doesn't look too fun. So what ends up happening here, as we plug more and more numbers into this value, we're not getting to a specific value. So notice that over here, we started plugging really big numbers in. We got really close to this horizontal asymptote. When we plug numbers in over here, we got really, really close to 0, the horizontal asymptote. Well, over here, we don't have a horizontal asymptote. What we have is an oblique asymptote. So the way that we find our oblique asymptote, so I'm going to cross this part out and say oblique asymptote. So to find the oblique asymptote, we have to do long division with our function to see where our graph ends up going. So let's start our x plus 1, 2x squared plus 3x minus 1. And let's see what that asymptote is going to look like. So what do we multiply to x to get it to look like 2x squared? We multiply a 2 and an x. 2x times x is going to be 2x squared plus 2x, and we're subtracting all of that. So let's change the sign to everything to make it a little bit easier to add. So that's going to be 0, that's going to be x, and then bring that 1 down. And what do we multiply to x to make it look like x? Well, technically nothing, but we're going to multiply it by 1. And that's going to be our x plus 1. Put that in parentheses and subtract it. Let's change the sign to everything to make it easier to add. 0 and -1 plus -1 is going to be -2. So we have 2x plus 1 plus -2 over x plus 1. And this is y is equal to that function. So this is our actual function right now. And as we start plugging in really, really big numbers, remember when we have our variable in the denominator, it kind of pushes this value here to equal 0. So as we plug really, really big numbers in there, this starts to be less and less convenient for the graph. Well, not convenient. It's less and less, I can't think of the word right now, but this is less and less important to the actual function of the graph. So this here ends up being our oblique asymptote. So x or y is equal to 2x plus 1. That's what we're going to graph as our oblique asymptote. And here, y-intercept of 1 going up 1, 2 over 1. Going up 1, 2, and over 1. That there ends up being the oblique asymptote that we need. So I know it looks weird, but after we graph the rest of this, then we'll kind of talk about, we'll graph it on Desmos so we could see what it looks like. But that is part 2 or step 2 for graphing our rational functions. Let's move on to step 3. Step 3 is finding our y-intercept. Back to the easy stuff. Our y-intercept happens when x is equal to 0. So we're going to evaluate our function at 0. So 2, 0 squared plus 3 times 0 plus or minus 1 over 0 plus 1. So this ends up being -1. So we have when x is 0, y is -1. So let's graph that. When x is 0, y is -1. And let's find our x-intercept. So our x-intercept happens when y is equal to 0. So we evaluate, or we set our function equal to 0. X plus 1. Multiply both sides by that x plus 1. So we have 0 is equal to 2x squared plus 3x minus 1. And here we could factor, or we could just plug it into our quadratic formula. X is equal to -3 plus or minus the square root of 3 squared minus 4ac all over 2a. So -3 plus or minus the square root of 9 plus 8 over 4. So this equals -3 plus root 17 over 4, -3 minus root 17 over 4. Let's graph this. Not graph it, let's plug it in to see what those actual values are. So -3 plus the square root of 17. And let's get minus. So now we have this divided by 4 and this divided by 4. So those are our two values. So we have -1.78 and 0.28. So we have those two values, -7 or -1.78, that's -1, -1.78, that's -1, -2, 7, 8 is about here. And also 0.28. So 0.28 is going to be somewhere about here. All right, that's step number 4. Let's go on to step number 5. I feel like we're almost done here. So step number 5 is, does it cross our horizontal asymptote? So it's not going to be our horizontal asymptote. This time it's going to be our oblique asymptote. So we're going to set our function equal to our oblique asymptote. So our oblique asymptote was our 2x plus 1 is equal to our function 2x squared plus 3x minus 1 over x plus 1. And if that's the same blue. Close enough. Okay, so now to solve for this, we're going to multiply both sides by this denominator to rationalize it. On the left side, we have a binomial times a binomial. So let's be careful with that. So we have 2x squared plus x plus 2x plus 1. On the right side, we have that 2x squared plus 3x minus 1. And let's see, let's move all the variables over, or let's combine like terms. 2x squared plus 3x plus 1 is equal to 2x squared plus 3x minus 1 minus 2x squared. Let's move all of the variables over to the left side. 3x. So over here, these two subtract out. These subtract out. So what we're left with is 1 is equal to -1. And since 1 is not equal to -1, we have no solution. So no solution for step 5, which means we don't cross our oblique asymptote. So now let's see for part number 6, our pick more points. So pick more points. Let's see if we have to pick more points or what points we should pick. So we know we're never going to cross our vertical asymptote because that's where our function's undefined. In step number 5, we found out that we're never going to cross our horizontal or our oblique asymptote. So we know that we're not going to cross there. We have 2 points, so we could connect here. So going along both of the asymptotes, we have that. And over here on the left side, we actually have a point here. So we technically don't even need our pick more points. So our function does something like this. And now I promised you that we were going to graph this just to see what it looked like. So let's give it a shot. Give me just a second so I could type it in. Okay, so here we have our function typed in. And let's kind of throw in all this other stuff we have. So we have a vertical asymptote at x equals -1. So let's type in x equals -1. And let's try that again. There we go. X equals -1. All right, so that looks good. Our horizontal asymptote we didn't have, but we did have an oblique asymptote. Let's try that. Y equals 2x plus 1. And notice how we have that. So it starts getting closer and closer to those 2 parts there. We have that oblique asymptote. Our y-intercept, we have that point 0, -1. 0, -1. There we go, much better. So 0, -1 for our y-intercept. Our x-intercept is a little uglier. So we have -3. There we go. So we have numerator -3 plus the square root, so SQRT. SQRT. So square root of 17 divided by 4. That's x, and then y is 0. And we also have the complement. Well, not the complement, but like the opposite, the minus. There we go. And those are those 2 points right there. Y-intercept, does it cross our horizontal, in this case, our oblique asymptote? No, we checked that. Our pick more points, we really didn't even need them because we had this part of our graph here, that part of our graph there. We didn't need any more of our pick more points. So there you go. That's how we were able to graph this function. And that's actually all of the examples that I have for you. If you need more examples, if you need me to post more videos, please just ask and I will do. If you have any questions, please let me know right away. If not, bye.